Hello students, welcome to the class. Today we will see the theory part 2 of the chapter Structure of Atom. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that the parts of the content may have been generated using the generative AI, which is experimental. Our objective would be today to describe the Thomson, Rutherford. Okay, so we will see these two models today mainly. If I talk about the topics specifically, then first would be Thomson model of atom. Second is Rutherford's nuclear model of atom. Third is atomic number and mass number. Fourth, isotopes and isobars. Then we will talk about the drawbacks of the Rutherford model. Lastly, we will see some problems related to this. So we will see problem number 2.1 and 2.2. So we have already learned about this Dalton's atomic theory. In today's class, we will see the next atomic model. So this Dalton's atomic theory was covered in the first chapter, some basic concepts of chemistry, but it failed as it was not able to explain the reaction part. So for that reason, and due to some latest experiments, we moved on to the Thomson model of experiment of atom. So let us try to understand what is this Thomson model of atom. So J.J. Thomson in 1898, he proposed that your atom is of spherical shape, right? And its radius was approximately 10 to the power minus 10 meter. Okay, just wait for a while. I will be back within minutes. Hello, Kaushal, is it clear now? So everyone was complaining about the voice. Is it loud enough? Okay. So let us start. So what we are talking about? We were talking about the Thomson model of atom. So Thomson model was saying that we have a spherical shape, right? We have a spherical shape of the atom and its radius was approximately 10 to the power minus 10 meter. And in that spherical shape, the positive charge was uniformly distributed. Uniformly distributed means in every part of the atom, there was equal amount of positive charge that was present. Okay. Now, then he said that, okay, we have a bed of this positive charge and in that bed, the electrons are embedded. And this positive and negative charge was contributing in the total stabilization of the atom. And this was the electrostatic arrangement that Thomson argued. Now, there are many different names given to this model in relevance to our daily life, like the plum pudding model or the raisin pudding model or the watermelon model. Now, why are they given to this model? You can understand this thing with the help of this image. So there are some spherical balls that are present inside this yellow area. They are representing the electron, whereas this whole part, okay, this whole big sphere, inside this big sphere, we have positive charge that is spread uniformly throughout the region. Clear? And this was compared to the watermelon, because in the watermelon also we have a red part. So you can consider that red part as the positive charge, and the seeds that is present inside the watermelon can be considered as the electron. So very simple model to understand. I guess we don't have we don't have much to discuss upon this Thomson model. Now, before moving on to the Rutherford model, we have to first understand that what is alpha rays and beta rays and gamma rays, because there you will see the inclusion of these rays. Okay, you will see the inclusion of alpha rays specifically. Beta rays was already used in the previous class, if you remember. So there was there was a word that was using the beta rays. So now we will first of all try to understand these three rays. So these are important. Questions are from there. You will see questions from alpha rays in the exemplar also. If I simply tell that what is alpha particle, then you can take a helium atom. Just take a helium atom and remove 2 electrons from it. Now, if you talk about helium atom, it contains 2 protons, 2 neutrons and 2 electrons. If you remove 2 electrons, what is left? 2 protons are left and 2 neutrons are left. Now in the previous class, we already know that 2 protons have a charge of +1, +2, okay? Because each have a charge of +1. Got it? So simply, you can tell your alpha particle as the helium 2+ particle. Now, talking about the characteristic of this alpha ray, it has a very high ionizing power, but a low penetrating power. What is this mean? What is the meaning of this low penetrating? Means if you hit your alpha ray against something, then it won't be able to pass through it. So it is so weak that it cannot even pass a piece of paper or a skin. Okay. So this is the meaning of your low penetrating power. Third thing, alpha ray are emitted during the radioactive decay of some heavy element. So whenever you will learn the nuclear physics, there you will see that alpha particles are being emitted in a radioactive decay. So two things are most important that I would say about alpha rays. First, what are alpha ray? It is a stream of particles, and those particles are helium 2+, and these particles have a very low penetrating power. Got it? Okay, now moving on to the next ray, which is our beta rays. What is beta rays? So this is something that is having high speed electron, or it can be positrons, both. So either it can be high speed electrons or it can be positron, both can be considered as your beta rays. And how it is emitted? Again, these alpha, beta, gamma, all these three rays will be emitted during the radioactive decay. What is the charge that is present on it? If you just go back and see the charge on the alpha particle, it is 2+. Here the charge is -1 or +1. Okay, what is positron? So a very complex term to understand. If I tell it in simpler term, then it would be a part of nucleus. Okay, a part of nucleus that is responsible for its charge. Okay, just a small part of nucleus. Or if I talk more specifically, then it is a part of proton that has the same mass as the electron, but a charge of +1. So that thing can be considered as a proton. Not the whole proton, because the proton has a very high mass. It is a small part of proton which has a +1 charge. As simple as that. Now this meaning is not literal, but for now it is good to go with. So see, it is written that they have a single negative or a single positive charge, but their mass is very small as compared to the proton or neutron. If I talk about the penetrating power, then it has a intermediate penetrating power. Now it is intermediate in which two rays? So alpha ray has the least penetrating power, then comes your beta rays. Okay, so it can pass through the paper, but it is stopped by a thin sheet of metal. Now next, it has a moderate ionizing power. So the charge is not concentrated on a small part of a proton. So basically, what happens in a radioactive decay? There is a conversion of proton to neutron. Okay. Now in that conversion, it emits the beta rays, beta plus rays, so that the charged part of the beta ray can be removed in a way, and we can only get a neutral particle. Got it? Now, what is the meaning of ionizing power? So, ionizing power means whenever you hit this particle with a different atom or a molecule, it can kick out the electron or it can ionize it. So, heavier is the mass, greater is the probability to ionize the other given molecule or atom. So, that thing is called as the ionizing power. Our last one is the gamma rays. Now, gamma rays do not consist of any particle. They are simply high energy, neutral and electromagnetic radiations, similar to the X-rays. So they don't have any charge. They don't have any mass also, right? They are simple neutral electromagnetic radiations, but of very high energy. So it is written that they do not consist of particles, and since they are invariant of particles, they have no charge or mass. Now, it has a very high penetrating power, right? It has a very high penetrating power. So this is the order. Alpha rays has the least penetrating power, then comes the beta rays, and lastly comes your gamma rays. Now, if we are good to go with this alpha rays and beta rays, then we can understand this Rutherford's experimental setup. So there are few parts of it. We will try to understand them one by one. Let's see. So anyone is having difficulty with the voice? Is it too low? Okay. So I will try to speak louder, which is okay. So what is the Rutherford's experimental setup? What he did, he took the alpha particles. So we know that alpha particles are emitted from the radioactive decay. So for the emission of alpha particles, he has taken a radioactive source. Now, he directed this alpha particle onto a thin foil of gold metal. Its thickness is around 100 nanometer. Got it? So what Rutherford did? He directed this alpha particle on this thin foil of this gold metal. Now, the thin foil of the gold metal had a circular fluorescent zinc sulfide screen around it. So behind this gold foil, he kept a round type of screen. So we'll see it. And when the alpha particle struck the screen, a tiny flash of the light was observed at that point. Now, what is the meaning of this? So suppose this is your source of alpha particle. The reason behind it would be, so you must have heard that gold is very easy to bend, or you can say it is very ductile. So it is easily penetrable, right? So due to that property, and plus due to the neutral nature of gold, so gold is very less reactive. So due to that reason, he must have taken gold. Okay. Now we have a source of alpha particle, a lead plate. What is this lead plate is doing? So it is making this ray a much more thinner. Okay, so maybe the alpha particle would be moving with a large area, so it would be covering a large area. Suppose it would coming from here, from here. Now what this lead plate is doing, it is absorbing most of the alpha particle and letting only a small amount of those to get through the hole and hit this gold foil. Got it? Any doubts? Now behind this gold foil, or you can say around this gold foil, we have this photographic plate which is called as fluorescent zinc sulfide. Remember, this is the same fluorescent zinc sulfide that can glow when heated with a charged particle. Now we know that helium-2 plus is a charged particle. So if this alpha rays hit this fluorescent zinc sulfide, then it would glow, and hence in this way it is acting as a detector. It is detecting that where the alpha particles are hitting after striking this gold foil. So this was the experimental setup of this Rutherford. Now, what would be the expectation if the Thomson model of the atom was true? Suppose if Thomson model of the atom was true, then what would be the expectation? No, it is not used as a colorimeter. So we are not doing that because alpha particle is not a radiation. It is not vibrating in say different planes. So basically what are we trying to do? So after the emission of this alpha particle, they may be hitting the zinc sulfide plate directly without hitting the gold foil. It may be possible. So what we are doing with the lead plate is that we are channelizing it. We are making a channel out of that whole rays of that gold part of that alpha particle, a small rays. Okay. Now, if the Thomson model was true, then what would happen? Then your alpha particle would be reflected back. Okay. So every alpha particle would be reflected back. And why it is so? Because according to Thomson model, whole of the atom is a positive charge, a bed of positive charge. Now helium-2 plus is a positive charge, is positively charged, and your atom is also having a bed of the positive charge. They will repel each other, and hence there will be complete deflection. So this would happen if the Thomson model was true. So it is written that alpha particle would pass directly through such a uniform distribution if it was true. So two cases are possible, right? First case is that they would have deflected, and second case is that if the mass is distributed all above, so it is written in the Thomson model that the mass is distributed, then since alpha particle have a small penetrating power, but if that mass is distributed, that wouldn't be a difficulty for the alpha particle to penetrate. So it would penetrate. So two cases are possible. Either all of them should penetrate, or if it is deflecting, then all of them should deflect. Now, it is written that it was expected that particle would slow down and change its direction only by a small angle as it passes through the foil. So we can take the helium-2 plus particle only because it is having an adequate amount of penetrating power that is required for the experiment. And it is having a proportionate amount of kinetic energy also. Got it? If we take some other particle other than the helium-2 plus, it was possible that due to its large size, it would have been facing difficulty to perform the experiment adequately. So is this thing clear to you? So what was said that if the Thomson model was true, then the alpha particle should have passed directly as the mass is distributed uniformly, or it would have been reflected due to the positive charge if the penetrating power was not equal. But what was seen? So the observation of the scattering experiment was First of all, it was seen that most of the alpha particle passed through the gold foil undeflected. So they passed directly. Second, a small fraction of the alpha particle was deflected by a small angle. And third observation was only a few alpha particle, right? Only a few alpha particles. So you can say it out of 20,000, one alpha particle was bounced back. And it was bounced back by an angle of 180 degrees. So these 3 points can be understood in the terms of this diagram. So you can see that most of the lines that are indicating the alpha particles, they indicate that they are passing directly. Okay. Now, some are deflected by a small angle, it is shown here, and some are deflected right back. Okay, so you can see that they are deflected back. Now, these are the 3 results we got, and these 3 results do not go hand in hand with the Thomson model, because Thomson model say that your whole atom, which is this, is having a uniform distribution of positive charge. If it is having a uniform distribution, then all rays should have behaved similarly. Got it? This should be the case. Now, on the basis of this 3 results, he gave his new model of the atom, or the nuclear model of the Rutherford. What was that model? We will see it. So let us just first of all conclude this Rutherford scattering experiment. What are his conclusions on seeing the observations? First is that if most of the alpha particle are passing directly, because they are not getting deflected, they are passing directly, it means that inside this atom, most of the space is vacant, and that is allowing our alpha particles to pass directly. So this is the first point, and this is the first conclusion he made from the observation. So alpha particle, your helium has, so see, if something is required in an adequate amount for a given thing, then you would do the same thing, right? Suppose if you are say stitching your clothes, then you will use a needle. If you are cutting a vegetable, you will use a knife. So similarly, for that experiment, alpha particle was the most adequate one. So he would have performed a multiple series of experiments. Then at the point of this helium 2 plus particle, he got his conclusion, right? So you can think of that this is a series of the experiment. Now, second was only a few alpha particle was deflected. This means that the deflection must be due to the enormous repulsive force. And what would be that repulsive force? It must be the positive charge. Okay. So the positive charge is now not distributed uniformly. It is present in a small area that is responsible for this deflection. And that area is very small. How I can say that it is very small? Because after some small deflection, we can only notice a few. It was written this, out of 20,000, one was deflected at an angle of 180 degree, means directly backward. So it says that not only it is concentrated in a area, it is concentrated in a very small volume. Got it? Now, with the help of calculation, he found that the radius of atom was about 10 to the power minus 10 meter, and that of nuclear was 10 to the power minus 15 meter. Now, this difference is very large. It may look that this difference is very small in terms of number. So you can think of this as a cricket ball that is placed in the center of a stadium, which is about 5 kilometers in radius. So that much small is the nucleus as compared to the total volume of the atom. And that is the reason we are seeing only a small deflection and a small amount and a very small amount of total deflection. Got it? So these are the conclusions of this Rutherford nuclear model of atom. Now, on the basis of this conclusion, he gave his nuclear model of atom. So the first point he made was that the positive charge and most of the mass, okay, two things, both positive charge and most of the mass is densely concentrated in a very small region. And he named that portion as nucleus. So this nucleus name was given by Rutherford. And why he said that the mass and charge are both concentrated in a small area? Same reason, because only a small amount of, I would say, out of 20,000, only one alpha particle was deflected in 180 degrees. Second was that the nucleus is surrounded by the electrons. Okay, and they are moving at a very high speed in circular paths called orbit. So you can think of Rutherford's model similar to the solar system, where the nucleus plays the role of the sun and the electron is the revolving planet. So what he did, he compared his nuclear model with the planetary model. Now, there must be a force to hold this electrons and nucleus together. So it's very simple. Your proton is positively charged, electron is negatively charged. So that force must be electrostatic force of attraction. So anyone has any doubt till now? I guess these things are simpler. But when you will see questions on it, given in the example and given in the exercise, you may face difficulty. So anyone has any doubt? So it's very simple. Electrostatic force is basically the force between two charges. So whenever we have two different charges, positive or negative, they attract each other. Why do they do so? Because if they attract each other, they would come closer and finally they would collapse and result in a neutral condition. Okay, but that is not seen in case of the say electron and proton in the atom. Now moving on further. So this is very, very important. The calculation of the atomic number and atomic mass and the representation of an element. Let us see how. So the thing is that why is electron and proton, although they are attracted to each other, they do not get close to each other and stick together. So I have discussed a little about in the previous class. So there is a thing called nuclear forces. So this nuclear force come into play when the distance between the charged particle is very, very less. Okay, they don't come into play on a larger distance, but as soon as the distance gets smaller and smaller, they grow exponentially, and this force is very, very large. And second thing is that if something is rotating, then there must be a centripetal force. Okay, we will see this derivation and all. So to counter that centripetal force, we have the electrostatic interaction. Now this two centripetal force and the electrostatic force of interaction are being balanced in such a way that they do not get stick to each other, neither they fall out of the atom. So there is a very small amount of, I would say, a very delicate balance between these two types of forces. We will study about this. Now, coming back to the topic, atomic number and atomic mass and their representation. First of all, you must understand that what is nucleons. So very simple. We know protons, we know neutrons, and in an atom, they are collectively known as the nucleons. So this is the meaning of nucleons. Next is, what is atomic number? So there are certain terminologies. Just get through this. These are important. We will see questions on it now. So what is atomic number? It's very simple. It is the number of protons. And it is represented by the letter capital Z. Now the thing is that the number of proton is equals to the number of electron, but it is only true in a neutral atom. So remember it. Whenever you write the definition of atomic number, and if you are considering the number of electron, it should be in a neutral atom and not in a charged atom. So what we can say, summing up our whole thing, that atomic number is equals to the number of proton is equals to the number of electron in a neutral atom. Second thing is the mass number. Again, very simple. The total number of particles that are present inside a nucleon is termed as the mass number, and it is represented by the capital letter A. How do we calculate it? So I said it is the total number of particles present in a nucleon. So it would be simply number of proton plus number of neutron. So this is never true. Proton is not equals to neutron, and it is true in most of the cases you will see it, but do not take it for granted. Why I am saying it? Take it the example of hydrogen. They have one proton, they have one electron, but they do not have a neutron. Means the proton count is not equals to neutron. So remember this thing always, that the number of proton may be equal to neutron in most of the atoms, but it is not always true. Now mass number is simply what? Number of proton plus number of neutrons, which is simply the number of nucleons. How we will represent the atom with the help of this atomic number and the mass number? Suppose our element or the atom is having X as its symbol. So write the X here and write A on the top side, which is your atomic number, and Z, which is the A, which is the mass number, and Z, which is the atomic number, on the bottom right and the bottom left respectively. In this way, you can represent a given element. So this is a very simple representation. Now, if you know about atomic number and you know about the mass number, then we can move on to the isotopes. So what is isotopes? They are atoms which have the same atomic number. Okay, means they have the same number of protons, or we can also say they have the same number of electrons in a neutral atom. But if the number of electron is same, then what is different? Their mass number is different, which is represented by the capital letter A. So what we can say? That they have different number of neutrons, and as a result, they don't have the same mass number, because the atomic number is already same, but the mass number is different. That means your neutrons count is not same, or you can also say the count of nucleons is not same in the isotopes. Third thing, since they have the same number of electron, therefore their chemical properties are same, because the chemical properties of a given element is almost decided by its number of electrons, because they are responsible for its reactivity. But due to change in the mass number, which is simply the mass of an atom, it can show different physical property, like its density can be different, okay, its volume can be different, mass can be different, even radioactivity can be different. So this point is very important. Isotopes have the same chemical properties, but different physical properties, including mass and radioactivity. The example of it would be hydrogen, which has 3 isotopes. One is protium, then deuterium, and then tritium. I have represented using its representation. You can see that hydrogen has a mass number of 1, which is protium, then deuterium has a mass number of 2, and tritium has a mass number of 3. Now all of them have the same atomic number, which is 1. Therefore, each of them will have 1 proton. Got it? But what about the neutron? So 0 neutrons are present in hydrogen's isotope protium. So this is the only example in the whole periodic table which is having no neutron. Okay, protium is the only example. Then In deuterium, we have 1 neutron, and in the tritium, we have 2 neutrons respectively. We can have more examples of chlorine. If it's your choice, you can go and look for the chlorine also. It is also more than one isotope. So is isotope clear to all of you? Then we will move to the isobars. What are isobars? So they are different element. Okay. So isotopes are same element because their atomic number is same. Their mass number is different, but they are different element having same mass number. Now, what is mass number? It is simply the summation of protons and neutrons. Okay. So if I just conclude it, then I would say that isobars are those elements which have the same number of proton plus neutrons, but they have different number of protons and neutrons. Second thing, since their count of electron is different, that means their chemical properties will obviously be not same. And they all will belong to different elements because electrons are responsible for the chemical reactivity of each and every element. For that reason, chemical properties of the isobars will be completely different. The example of it would be argon and calcium. You can see that they have the same mass number of 40, but argon has an atomic number of 18 and calcium has an atomic number of 20. Now you know it very well that calcium and argon have very different chemical properties. So what you would say about calcium and argon? I would say that calcium and argon has the same number of protons plus neutrons, but they have different number of protons. So our important point that we should conclude from these two slides is that chemical properties of atoms are concluded by the number of electrons. Okay, and therefore number of neutrons have a very small impact on their chemical reactivity, and hence isotopes have a similar chemical properties or similar chemical behavior. Okay. Now we will do some questions on it. The first question is here for you. You have to calculate the number of protons, neutrons, and electrons in the bromine, whose description is given here, or the representation is given here. How will calculate it? So I am giving some time to solve it for you. Just calculate the number of protons, neutrons, and electrons. So anyone who is willing to give the answer, just the comment in the comment section. Let's see if it is true or not. So what will be the number of protons, neutrons, and electrons in the given element? So I guess 60 people are there in the lecture. I would expect more answers from you. Okay. Now let's see. It's a very easy one to do. Yes, the upper one will be atomic number. It's very easy to understand that because atomic number is the sum of number of number of proton plus number of neutron, whereas the atomic number is simply the number of proton. Obviously, mass number will be greater. So this one is the mass number. So the first question is very simple to answer. Since the number of proton is equals to the atomic number, therefore the number of proton is equals to 35. Okay. What will be the number of neutron? I guess it's very easy to do that. You know the total number of proton, you know the number of proton plus number of neutron. Therefore, the number of neutron would be 80 minus 35. That would give you 45 as the total number of neutron. Okay, so this is the answer. Now moving on to the next question. The number of electrons, protons, and neutron in a species are equal to 18, 16, and 16 respectively. Assign the proper symbol to the species. So your time to solve this question starts now. I guess it's a very easy question again. So what will be the mass number and atomic number? Just write it for each for this given element. Yes, very good. So 32 and 18. Let's see if it is true or not. Anyone else who is willing to give the answer? Now, what will be the atomic number of the given atom? It will be simply equals to the number of proton. So that is given as 16. Okay. Now, if it is 16, that means your element is sulfur. Yes, the electron and proton are obviously same. Okay, yeah. So it will be 16 and 16. So this is the number of neutron, I guess. Okay, so there's a charge on it. So we can have a charged particle, right? It's true, right? Yes, it can be charged also. Now, what is the atomic number? Number of proton plus number of neutron. So this thing is checking that whether you are very clear about the atomic number definition or not. If you would take this 18, then you will get a wrong answer. If you take 18 as the atomic number, then you will get a wrong answer. For that reason, they have asked this in a way. So they've asked for the sulfur 2 minus rather than the sulfur. So coming back to the atomic mass, it will be simply 16 plus 16. That will be 32. And what is the excess electron they have? It is 2. So they have 2 excess electron. That means they will be negatively charged. And hence, it is an example of anion and not a neutral atom. So this will be the direct symbol of the given element. So I guess it's a very good question to solve, because student may do the mistake of ignoring this extra amount of electron, which is represented here by writing it as 2 negative. So anyone has any doubt in this question? Okay, moving on further. Now we will see that how this Rutherford nuclear model of atom was similar to the planetary model of the atom. So what he did, he small scaled the solar system and compared it with the lighter particles system, which is the nuclear system. Okay. If it is true, then in classical mechanics, we know that the planetary motion is there because of the presence of this gravitational force between the large celestial bodies. Okay, so I will not get into this. If it is known to you, good. If it is not known to you, there's no problem. You can easily catch up with the rest of the things. Now, similar to this interaction, which is based on the gravitational forces, our forces between the lighter particle are a product of the electrostatic interaction. Now, we know that electrostatic force is given by the equation k q1 q2 by r square, where k is the constant, okay, which is 1 by 4 pi epsilon naught in space. Q1 and Q2 are the charges and r is the distance. So he used this equation to explain the stability of the given model by Rutherford. Then the difficulty was that if a body is moving, okay, if a body is moving and if it is changing its direction constantly, it means that it is accelerating. Why I'm saying it? Because we know the definition of velocity. So whenever we say that if something is moving with a constant velocity, means it is not changing its direction first, and second thing, it is not changing its speed. But when an electron is moving in a circular path, although it may have the same speed, but due to the change of the direction, it is changing its velocity. Okay, and as a result, we can say that the particle or the electron is under acceleration, because due to change in the velocity, there will be acceleration. Got it? Any issue with this point? So it's very important to understand. And this was the main reason why the Rutherford nuclear model of atom was dropped. Now, if I am saying that, okay, the electron is moving in a circular motion, and due to this circular motion, the direction is changing constantly, and as a result, it is accelerating. What we can say further? We can say, according to the Maxwell's electromagnetic theory, that if it is changing its direction or if it is getting accelerated, it will emit electromagnetic radiation. So we'll learn about this Maxwell electromagnetic theory in the physics, where you will see that if a charged particle is accelerating, then it would lose energy, and it would lose energy in the form of electromagnetic radiation. Now, why it is not applicable for the planetary particles or the planetary celestial bodies? Because they are uncharged, but our electron is charged. So this is the difficulty with the direct analogy of your planetary model with the nuclear model. Now, if it is true, then electron would continuously emit energy or continuously emit radiation, and as a result, it will continuously lose energy, and finally, on losing all of its energy, the electron will drop in the nucleus, or it will sink in the nucleus, therefore collapsing the whole atom. So Rutherford model was first of all not able to explain the atomic stability as a result. Now, next thing, if the electrons were stationary, okay, if we do not consider the circular movement, suppose they are stationary, like in the Thomson model, then in that case, what will happen? The electrostatic interaction will pull the nucleus and the electron together, and ultimately they will collapse. Means they can't revolve around, nor they can stay in a specific position. Both can result to the collapse of the atom. Next major setback for the Rutherford model was he does not explain the distribution of energies, okay? That how the electrons are present around the nucleus. He said that they are revolving around the nucleus, okay? But what is the position of that electron? How are they present? Are they present at a distance of 2 nanometer, or are they present at a distance of 200 meter? That was not explained by the Rutherford. If this was not explained, then we cannot guess the energies also, because we are unaware about the distance and about the force. So again, I am repeating the whole set of drawbacks. Two drawbacks are there. First is, according to the Maxwell's electromagnetic theory, if any charged particle is under a constant acceleration, then it would emit radiation. Now, our electron is revolving around the proton. Electron is negatively charged, so it is a charged particle. And since it is revolving around, it is changing its direction constantly. That means it is under acceleration. So, according to this Maxwell theory, it will emit electromagnetic radiation. Now, if it will do so, that means it is radiating energy, because electromagnetic radiation is a form of energy. Now, finally, it will lose all of its energy and fall into the nucleus. So, this was questioning the Rutherford model, because in this situation, the whole stability of the atom would be gone. Now, if I take the second case, suppose that our electron is not moving, it is there at its position, still not moving. Then again, the proton will be attracted towards the electron, and the electron will be attracted towards the proton. Now, finally, they will stick together, and that would again result in the collapse of the electron or collapse of the atom. Due to these reasons, the Rutherford model was not accepted. Now, the last setback, which was there, was he was unable to explain the distribution of energies, that how the electrons are distributed, at what distance they are present from the nucleus, what is their corresponding energy. All of this was not described in the Rutherford model. So this was all for today's class. I hope you enjoyed the lecture. We will meet again in the next session. Okay, before ending this lecture, I want to explain one thing. So there was a diagram that we saw earlier, okay, which was explaining the, say, our Thomson experiment. So there is a small change in the diagram, although it is given in the NCERT. So the poles of the magnet will be changed. So north was given here and south was given here. So this would be reversed. South will be here and north would be here. Now why it is so, I will explain it later. What you can do by yourself is just try to apply the Fleming's left hand rule, okay, and get the direction of force where the electron will hit. So if you do that, you will see a disparity. So I am first leaving this thing to you to understand the Fleming's left hand rule. Then I will explain that why the image that is given there is wrong. Okay. So thank you for attending this lecture. We will meet tomorrow.